Hi everyone, Mr. Mark here. Today's video we're going to be looking at exponential regression, which is the last part of the bivariate statistics topic in Year 12 General Maths. Previously in this topic we've been looking at the relationship between two sets of numerical data or two sets of numerical variables and showing the relationship with a least squares regression line or a line of best fit essentially. But we've also got to the point which we've discussed when it's not appropriate to use that linear model to show that relationship between those variables. In particular, we got to a point where we did a residual plot. And when a residual plot shows a clear pattern, then we are not going to be using that linear model to show the relationship between those two variables. Or it's not appropriate to use a linear model to show the relationship between those two variables if there is a clear pattern on our residual plot when we're looking at the residual values from that least squares regression line. Okay, and I've shown you that process in previous videos. So this example is showing the population of elephants declining over a period of 5 years. And although you can see this line of best fit, this least squares regression line sort of sits well through those points, when we create a residual plot, you can see a clear pattern. So that suggests that the linear model is not appropriate for this set of data. So in that case, we're using an exponential model. I'll get to that in a second in terms of an example, but a bit of, I guess, prior or assumed knowledge from the Year 11 course when we're looking at exponential models. We'll be looking at the exponential model in the form of y equals a times b to the power of x, okay? Where a and b are constants and b needs to be greater than 0. A is just simply our y-intercept, okay? So a is the value that line, that exponential line, will cross the y-axis, okay? And b tells us what percentage y is increasing or decreasing for every one increase in the x value, okay? So if b is equal to 1.23, we're talking about a 23% increase in the y value for each x increased by 1. And if b is less than 1, so it's still going to be greater than 0, but if it's less than 1, it's showing a decrease in that y value for every x increased by 1. So if, in this case, b is 0.89, then it's actually showing an 11% decrease in the y value for every increase in the x value by 1. If, for example, b equaled 0.65, then it would be showing a 35% decrease. Okay, so you understand that to get this 35% decrease, I'm essentially just subtracting that percentage from 100%, which in this case is converted to a decimal. So 0.65 plus 0.35 will take me to 1.0 or 100%. So that's where that relationship is between those two values. Okay, and hopefully that makes sense. Again, that's a little bit of prior knowledge from the Year 11 course. So moving into an example here, we have the mass of bacteria in a culture is measured each day for 5 days. So you can see our explanatory variable is the number of days, that's our x data, and the mass in grams is our response variable, that's our y data. Those values be plotted against the y-axis. So first thing it says to draw a scatter plot for m against t. Now save a little bit of time. I've already gone through this process and I've drawn that least squares regression line as it asks, just the scatter plot. And it looks pretty suitable. You can almost see a pattern starting to appear here, but it won't always be that clear. The next thing says the next part of the question says find the exponential model for the data in the form m equals a times b to the power of t, okay? Remember we spoke about this in the form of y equals a times b to the power of x. Well, obviously, t is our x value and m is our y value in this case. So rather than y equals a times b to the power of x, we've got m equals a times b to the power of t. Hopefully that makes sense. So in order to draw that exponential model, we're going to go through a slightly different process. I just want to show you as well though, based on the least squares regression line, I've actually calculated the values of r and r squared. and drawn that residual plot, you can see there's actually a very strong positive correlation based on our Pearson's correlation coefficient and our R-squared values, suggesting that there is a connection or relationship between those two variables. However, when I then draw that residual plot, we can see a clear pattern forming here, which suggests that the linear model is not appropriate. Okay. What I also did is I just copied those residual values in list 3 here, just so you can see those, because I'm going to compare those in a minute to the residual values for the exponential model. Okay. So how do we work out the exponential equation from this set of data? Again, once I've gone through and drawn my least squares regression line, and I'm back into the list form here. So I've got the data in list 1 for X or T, and the data in list 2 for M or Y. And there's my my residual values for the least squares regression model or for the linear model. But I'm now being asked to work out the exponential equation. From here, we go into F2 to calculate, and then we go onto F3 for regression. We're going to go across here, so F6 onto the next screen where it says exponential. If we click on that, and we're looking in the form of a times b to the power of x, okay, so F2, and these are the values that I'm looking for. And now you can actually see, if I scroll down a little bit here, that the linear model had an R value of 0.96, but the exponential model has an R value of 0.999. The R squared value for the linear model was 0.93 or 93%. For R squared, it's 0.999 or 99.9%, which is obviously higher in the exponential model than it is in the linear model. So again, that's some evidence that suggests that the exponential model is more appropriate in this case. Anyway, what we are looking for are the values of A and B to plug into this equation here. So A is equal to approximately 2.25, and B, as it says there, is equal to approximately 1.660. So in the form of M equals A times B to the power of T, we're just substituting those values of A and B into the equation here. So it becomes M equals 2.25 times 1.60 to the power of T. Now, the next thing it says, interpret those values of A and B. Okay, now we know that A is our y-intercept, but what does that mean in terms of the problem? Okay, so remember it was about the weight of the bacterial culture after a certain number of days. So what A tells me is that the initial weight of the bacteria was 2.25 grams. Okay, so initial weight, or initial mass, I should say, of bacteria was 2.25 grams. What about the value of B in this case? Okay, again, it's asking us to interpret in terms of the problem. And remember, this is our multiplier, and because this value of B is greater than 1, it suggests that the mass of the bacteria is increasing. We can see it's increasing from day to day. How much is it increasing by? Well, it's increasing by, in this case, 60%. So the mass of bacteria is increasing by 60% each day. Okay, so that's in the context of the problem, the meaning of A and B from this exponential model or exponential equation now. All right, it then says to predict the mass of bacteria in the culture after 7 days. So to do that, all we're going to do is we're going to substitute in T equals 7. So for that one, T equals 7, and substitute it into our equation, which was M equals 2.25 times 1.60 to the power of T. In this case, it's to the power of 7. So go ahead and throw that on your calculator. I'm just going to do that on my, my normal calculator. So 2.25 times by 1.60 to the power of, in this case, 7. So after 7 days, we'd expect the mass of the bacteria to be approximately 60.40 grams. Okay, so the mass is approximately equal to 60.40 grams to 2 decimal places. Okay, the last question here says, how long will it take for the mass of the bacteria to reach 100 grams? Now, I'm going to do that using the graphics calculator, and I'll show you how to do that right now. So we head back into the graphics calculator, and we copy. If we press copy, that copies the equation in terms of A and B. And I'm going to dump that into the graphing function here. If I exit the stats function and head then into the graphing function, the equation is there waiting for me. Okay, and you can see it hasn't rounded it off. It's got, I think about 14 decimal places there for A, for example. Anyway, that's fine. Let's select that and draw it. Okay, and what we're then asking for is, what is the value of T when M is equal to 100? Or what is the value of X when Y is equal to 100? So what I'm going to do is I'm going to do an X calculate. All right, so I do Shift G solve, head across to X calculate, put in my Y value of 100 and hit execute. Now, if it doesn't show, it's because the view window is not big enough. So this is where you need to be able to manipulate that view window, and that's an important skill as well. So once I'm in this graph, press Shift View Window, F3, and change the view window. Now, understand that I want to be able to see, at least, let's go up to 15, for example, on the X-axis, so 15 days. Because I know it's obviously going to be more than 7 days, because at 7 days the bacteria was 60 grams. So I want to turn my maximum on the Y-axis here. Let's make that 150. Obviously, it needs to be at least 100 to fit in. So hit execute. Once I've at least changed those two values, you can change the minimum values as well if you want. Go back and draw it. And then I go through that same process of Shift, G solve, F6, X calculate, type in 100 here, and hit execute. And then it should tell me that when Y is equal to 100, X is equal to 6.12. Sorry for zooming in so close. So 6.12 days is the answer there. So, sorry, let's just have a look again. Maybe I didn't zoom in close enough. It's actually 8.12. Of course, it's going to be bigger than 6 because we know that at 7 days, the mass was 60 grams, so it needs to be more than 7 days. So it's actually 8.12 days. So when we're looking for 100 grams is equal to 2.25 times 1.60 to the power of X. In that case, X is equal to approximately 1.2 days. So when will the bacteria have a mass of 100 grams? In approximately 8.12 days. Now, the other thing I just want to show you is that once you've, if I head back into the stats function, once you've drawn that, or gone through that process, of calculating those values for A and B in the exponential model, so regression, F6, exponential, A times B to the power of X, once you've done that, then and if you've set up your graphics calculator like I've shown you previously, in list 3 shows those residual values for the exponential model. Now, if I compare those values in list 3 for the exponential model to the values in list 3 for the residual values in the linear model, you can see these values are a lot smaller, meaning they're a lot closer to that model or that line, okay? So that there is another bit of evidence to suggest the exponential model is a better or more appropriate fit for this set of data. The other thing you can do is you can draw the residual plot for this. I will do it for you, but this one isn't the best. I've had a look at it already. So if I go back and draw graph 2, again, there shouldn't be a clear pattern. It kind of looks like there is a bit of a pattern here. That's why I'm saying this isn't the best example. But ideally, there wouldn't be a clear pattern showing here. They'd be randomly scattered over the x-axis, which then suggests, again, that this is an appropriate model for this set of data in terms of this exponential model is appropriate, okay? But again, this one probably is showing a little bit of a pattern. But I think, yeah, if you look at the list 3 there, how low those residual values are compared to list 3 for the linear residual values, you can see these are a lot lower, okay, meaning they're a lot closer to that model line. All right, so that's it for this video. Hopefully that helps, and there's a little bit of benefit to you in terms of looking at exponential regressions or exponential models in terms of the bivariate data. Okay, thanks for watching, and hopefully that helps.